All right. That was a great presentation from Andy. He's always a hard act to follow. When I heard he was going to be late, I was actually kind of happy because maybe I could just go ahead of him, and then I'm not going to just repeat everything he just said. But anyway, I'm from the San Diego Supercomputer Center. I was going to basically describe our installation of SAM-QFS and our basically our overview of our operations, and then some of the archival challenges we have, future requirements that we see, and then some emergent technology that may help solve some of those issues. So SDSC is part of the TerraGrid project. That's the National Science Foundation's coalition, basically, of large compute centers that are all interconnected with a high-speed interconnect or network, wider network. We are providing some compute systems for that, for the NSF. Today we've got basically 15 teraflops of Power 4 based processors, and with a Federation interconnect. We also have an IBM Itanium cluster that's kind of getting on in age, but it's got a MirrorNet switch interconnect, and then we also have the 17 teraflop IBM Blue GNL. Let's see. As far as data and grid computing goes, the TerraGrid is pretty useful in getting jobs to run, but then there's always the issue of how do you get your data there? Because basically a lot of these more data-intensive applications that are available have, basically data sets that are verging on the hundreds to petabyte size. So if you want to do something with that data, today's grid computing, you normally have to basically migrate that data over to the site you're going to use, and they have to have the space on that end. You have to take all this time to manage that whole process of getting your data over there just to run it, and then possibly store it back in some other facility, or maybe migrate the results of your simulation, your derived output, to some other post-analysis system to do visualization or just data mining efforts, and all that takes a lot of time and effort. Having a more centralized approach would obviously alleviate a lot of these issues. I wanted to give a quick example of one of these active projects that we have. This is the Southern California Earthquake Consortium, or Center, and they basically do large-scale simulations of what happens when there's a huge earthquake that hits the Southern California fault lines. Such as like a 7.7 that originates in Palm Springs, for example. The bad news is that the wave just continues to propagate between the ocean and the mountains, destroying all of LA, but maybe that's not a problem for some people. Anyway, so talking to them about their requirements, their run basically took about 5 days, and they outputted about 50 terabytes worth of derived data from their simulation, taking input from sensors that they had along the earthquake basin. It was an interesting project, actually, because we didn't have enough. We didn't have 50 terabytes of actual parallel file system space when they started their simulation. So we were actually migrating data off of the parallel file system as the job was running, just to try to keep up with it, and we were actually successful in doing that into the SAM-QFS. But then talking about their future requirements, they're looking at doing basically a petabyte size run. They're just looking, the obvious step is to increase the resolution to get a finer grained simulation and more accurate results. They're already planning basically a run on the NCSA machine named Abe, and they're planning to generate basically a petabyte worth of output. So there's many of these applications that are out there. It's definitely they're not all really looking for this kind of space requirement, but there's quite a few that are. This definitely the geosciences area, a lot of the like the astrophysics, the sky survey stuff, where you're taking telescopes and doing surveys of the night sky, looking for interesting effects. Something like the LSST project, which is going to be a huge microscope or telescope that's coming online, and is looking at generating petabytes of data. Of course, you got all the colliders and the higher geophysics community that are generating more output or generate more data in there than they can do anything with, it seems. So anyway, to try to provide these to provide resources for these projects, SDSC has put together a fairly extensive storage infrastructure. We've got over 2 petabytes of a spinning disk, mostly serial ATA based. We started out with fiber channel, but we have a large amount of serial ATA storage now. We also have a very large storage area network, about 1,500 ports. And then in order to store a lot of these results for long-term preservation, we have an archive based on 6 of the large SDK powder horn silos and about 100 fiber channel tape drives. And today we're running mainly IBM systems, so we're utilizing the GPFS file system to store most of the simulation-derived output. Let's see. So I'm going to actually see if I can switch this so I can look on the screen here. Sure. Oh, great. Okay, now I got both. Okay. Let's see. So the SDSC, we're actually running 2 archives today. We're running IBM's HPSS system and Sun's SAM-QFS. We have 3 staff, well, 2 staff really, and then me as a backup on SAM-QFS. We're looking to probably hire another. And then we've got roughly 5 petabytes worth of stored data today. We've got roughly 28 petabyte capacity. If we filled up all of the slots with our high density 700 gig media today. We have over a million or over 100 million files. One thing to note is SAM-QFS has more files than HPSS, even though it's storing less amounts of data. So there's a larger amount of small files. SAM-QFS seems to handle the small files better. Let's see, we're getting fairly decent transfer rates today, approaching 700 megabytes a second. Most of this is kind of bound by the client side resources that we have for actually doing transfers in and out of the archives. And then we're providing some offsite storage replication for disaster recovery. Some of this data is pretty much non-reproducible. When you're taking sensor data off of the earthquake basin, or even have somebody that's storing monkey eye sensor readings and stuff like that, you can't reproduce that. So we want to be able to ensure the integrity of that data by providing some offsite storage for that. Here's a kind of a breakdown of the centralized stand and storage architecture at SDSC. We basically have the TeraGrid 10 gigabit Ethernet network up here. We've got our main compute resources here in the middle. Most of them are directly connected into our large storage area network. And then we have this pool of fiber channel and serial ATA storage that is kind of divided up between all of these systems. And that's all shared as well by the 2 archives, got SAM-QFS and HPSS. HPSS today is also directly interconnected into the Federation network, which provides some fairly high-speed transfers between the 2 systems. One thing I haven't really talked about is GPFS WAN. Basically, we're able to export nearly a petabyte-sized parallel file system over the wide area network to our partners at TAC and NCSA, Argonne National Labs. There's large multi-thousand node clusters at these sites that are mounting this parallel file system here at SDSC, which is convenient because researchers can store their results in this parallel global file system and then turn around and access it immediately from another TeraGrid resource. Here's a more detailed picture of our SAM-QFS architecture. We just recently went to x86 systems for our metadata servers. We were looking at Spark, but basically the clock rate advantages of the AMD processor line really was a real improvement for some single-threaded aspects of the SAM-QFS file system itself. There's a few things that kind of go sequentially. So we got like 3 times the performance out of the AMD processor line. Plus the PCI Express and things gives us adequate I/O to basically handle the migration of data from the file system, disk cache, in and out of tape here. across the storage network. It actually goes up to the server and then back out to the tape. Then these other systems are just for some of our clients, like our compute systems that we have, mounting it over NFS today. We also have we do backups basically for our Oracle rack environment. We also do some web services here to provide web access to large data collections that are directly in SAM-QFS. We have some smaller project compute clusters and things. And then also that remote disaster recovery out to Pittsburgh. So this is just a quick overview of the way we have our tape silos interconnected. Everything has pass reports, so any tape could get to any drive location. We try to organize the media, obviously, so it's close to the tape drives that's going to be used. Simple things like that. Here's the kind of a diagram of one of the disaster recovery solutions that we have today. Basically, we're using the storage resource broker, which is some software middleware that's been developed at SDSC to manage very large data collections. It provides an infrastructure for tagging collections with metadata, being able to do replication, being able to share it in an open kind of grid way using the standard Globus security infrastructure. It has access controls. You can also have it integrate some workflow type applications, so that if you just want to maybe pull something out of an image, you can have that integrated into the kind of this virtualized storage infrastructure. It gives you a global namespace, so even though you have your files put on different storage systems, you can have one unified namespace to reference it all, and that doesn't change even if you move your data around. It's a pretty powerful application that a lot of our researchers use, especially if they have large data sets they have to deal with, or large communities of people that they're collaborating with. So we're actually using the SRB internally just to do this replication of data out to INCAR. They have something called the Match Storage System, something they've written themselves, that stores data off onto their tape silos. And the SRB server basically manages the transfer of data between the two. And we also have a setup out at Pittsburgh. We have a SDK silo that's installed out there, and today we're running tape drives directly through a fiber channel over IP gateway. That's proven to be not very good in terms of performance. The latency issues going over a wider network for tape is really too severe. We did prove actually that running regular fiber channel or serial ATA storage over those latencies is not really an issue. You can actually get line rate if you're interested in pursuing that for some reason. But tape technology just isn't really meant for that. So we're going to be moving to a dual server configuration, one handling HPSS, transfer data through HPSS, and the other one handling transfers through SAM-QFS with SAM Remote. Okay, and then one other thing we're doing to help us manage this environment is we're installing the Crossroads Read Verify appliance. Basically, provides some very nice active monitoring. There's a lot of data that you can get out of SAM-QFS, but you really have to kind of go get it yourself out of logs and other information. Maybe pull stuff off the server itself, or the switch statistics, or querying the tape drive, and yeah, all that data is there, and you could write something yourself. But this basically gives you an integrated look at a lot of the your tape activities, which will be interesting for us to see. It'll help us diagnose, performance problems, and possibly be proactive, or help us be proactive at fixing hardware when there's problems. It gives a nice read-write error per tape. It actually keeps track of that on a media basis. So then we can go and say, this media is starting to exhibit read and write errors. So let's go ahead and repack that data onto some other media, and make sure we don't, it's safe. We can safeguard our data, that kind of thing. And then it'll send out reports and alerts and things like that. Here's kind of a quick look at it, such as like tape load count. You can kind of see if you're getting the use out of your tape system, what your workload looks like, what parts of the time of the day are you seeing the heaviest load, that kind of stuff. So, I mean, I only have two archive system administrators today. They really don't have time to go and do all this, write all this reporting themselves. And of course, our management wants that kind of information for themselves. It'll help us do future procurement planning as well. You know, how active are our tape drives? What is our workload? How many new tape drives do we need to go buy? That kind of stuff. So I also wanted to give you guys an idea of our current usage, an idea of what we're working with. Most of our users basically store less than a terabyte of data into our archive. Most, 10,000 users, less than a terabyte. And then these actually represent a single user each. So we have basically about a dozen or so that represent the majority of the usage in our archive today. So we got one project with almost 300 terabytes, another with 240, et cetera. So we kind of focus on working with these projects directly and supporting their storage needs. So this is a logarithmic scale showing the kind of our growth since 1997. That's basically the inception of HPSS. And then this graph is a little outdated because it really kind of stops towards the end of 2006. I have another chart showing further progress, but the main thing to see here is that it's going up on an exponential curve. This is our kind of our planned capacity, but we're still seeing, like, we plotted two different lines, one that has a doubling every 14 months and another one that has a doubling every 15 months. So there's going to be an issue, obviously, because really financially and feasibly you can't really store exabytes of data in the future. It's just financially not feasible. So there's going to be a financial wall that we hit, and then we're looking at ways to try to deal with that. Here's a more up-to-date curve with this is where we actually deleted half a petabyte worth of data. That's why there's a break in that line, trying to save ourselves from repacking data that we didn't need. And then again, it's still growing in this exponential curve. Here's our challenges. I only have a couple minutes, unfortunately, left. But basically, we're seeing lots of issues with mixed files, large number of files, hundreds of millions to billions of files. Client transfer rates are a real issue because most of the hundreds of nodes generating data, but only a few that are actually trying to move data in and out of our archive. Small files don't really go onto media very well, so we have to end up repacking them. If small files are trickling in and you have a preservation policy that says within 30 minutes I need to get that off the tape, then guess what? If you only get a few small files, you're writing a few small files off the tape. So it's still not very efficient there. And then just like Andy was saying, the guys at CERN have really shown that there's a lot of data corruption that's kind of silent, that you don't see. And anyway, Andy's already just gone over all these future storage requirements. So I'm not gonna. I don't even have the time, so I'm just gonna go skip by that. And then, as far as emergent technologies that we see, we're really excited about flash and solid-state disk. We're actually using a Texas memory system, solid-state disk storage for our metadata under SAM-QFS, and it's really fantastic in terms of performance, especially when you're kind of dealing with a single metadata server configuration. We're really also excited about Lustre 2, basically the version that's coming out in late next year, that's going to have clustered metadata servers that'll help alleviate the kind of performance problems there with metadata, and GPFS already has clustered metadata servers. It's also great. I mean, you're getting 100,000 IOPS a second on 1 to 2 terabytes of solid-state disk. That kind of storage is becoming affordable with this new flash memory technology. Then you got serial ATA, but again, you need intelligent storage, especially serial ATA. There's really not checksums all the way through it. If you're not, even if you have RAID 6, most controllers only do the parity checking when it's writing the data and not when it's reading. There's intelligent controllers like the ones in DDN that actually recheck the your RAID calculation on read too, to make sure that the SATA disk wasn't reading the wrong blocks that time and giving you corrupt data. So things that's kind of important. Dual parity for sure because of the large rebuild times and that kind of stuff. So I really appreciate your time today, and I'm happy to answer questions.